in.
Va bene, sì, a posto.
Bene, possiamo cominciare se...
A posto, grazie. Io sto giù, che vi controllo su. Okay, so so the quantum phase space is this mathematical structure that encodes information about the space-time and the momentum space inspired by quantum gravity considerations. So, for example, in the semi-classical limit of quantum gravity, there appears some departures from classical equations that are described in the usual phase space, like modified dispersion relations. For example, there are some examples in the quantum gravity community. For example, quantum gravity, causal dynamical triangulations, Kappa-Minkowski non-commutative space-time, and Horava-Lifshitz gravity, for example. And there is the appearance of these modified dispersion relations that, as you can see, are modified by the presence of length or energy scale L that is usually related to the Planck scale, so it's of the order of the Planck length. Well, since we do not know what is the full theory of quantum gravity, we follow a procedure that parameterizes our ignorance about the, let's say, the full theory. So we propose a general modified dispersion relation and then begin to constrain the parameters to see what are the theories that are most favored or disfavored by data. Well, in general, this kind of approach presents an energy-dependent speed of light, but this is not necessarily the case, but usually this happens. Well, in this way of reasoning, these modified dispersion relations, you can think of them in two ways of the community is divided into two parts. You can think about in a Lorentz invariance violation scenario, the LID, because Lorentz transformations do not preserve a modified dispersion relation, the form of the modified dispersion relation. Therefore, there should be the appearance of a preferred frame that measures the Planck scale. And on the other hand, you can think about doubly or deformed, a deformed version of special relativity, in which the Lorentz transformations are deformed in a nonlinear way, such that it can preserve the form of the modified dispersion relation. Usually, in this scenario of deformed special relativity, to preserve the nature of the vertices of the interactions of particles, it is necessary to consider a modified composition law of momenta, such that all observers would agree about the nature of the conservation laws. This second example preserves the relativity principle. So, usually, this way of reasoning about ESR, one way of reasoning is by considering a curved momentum space. You consider momentum space as a curved manifold. So, this way of reasoning has an interesting interpretation in the recent years, from 2011, named relative locality, where the mass or the modified dispersion relation is determined by the metric of this momentum space as a differential manifold, and the composition law is related to a connection following those formulas. Usually, the Sitter space has been majorly considered in this literature for some reasons that I can describe in a moment. But the anti-de Sitter case has been considered only in 3 dimensions. Therefore, we wanted to feel, and also inspired by other assumptions, to fill this gap about the anti-de Sitter momentum space. So that's where this part begins. So the only quantum gravity theory that we managed to solve is the 3-dimensional quantum gravity, the 3-dimensional general relativity. Well, just resuming, it presents a DSR relativistic symmetry, and a curvature of momentum space of anti-de Sitter type. And this formalism is compatible both with the curved momentum space formulation of relative locality that I described and with the Hopf algebra structure. Well, so here we take exploratively as working assumption that also in the 4D quantum gravity, maybe the momentum space should appear in some limit. A curved momentum space should appear in some limit. And naturally, one way of thinking about this is the anti-de Sitter. So, we wanted to work on this subject using geometric tools. Then, we identified the basic properties of the 3D quantum gravity momentum space in this set, R1, R2, R3, and R4, that could also have B. Well, the first one is trivial. The second one basically states that composition law is a translation in this maximally symmetric space. And the third is associativity, and the fourth is covariance. That could be as the letter B, that is does not have back reaction, or the first case that has a back reaction on the rapidity parameter. Well, so these four properties not only are present in the 3D quantum gravity, but are also present in a particular formulation of the Sitter momentum space. The one that fits well with the Kappa-Poincaré or Hopf algebra that appears from non-commutative Kappa-Minkowski spacetime. So, we have the de Sitter case that appears in the non-commutative spacetime, the momentum space of the non-commutative spacetime, and this is worked for any dimensions. And for 3D gravity, there appears to be anti-de Sitter. So, we here conjecture, and both of these approaches are connected to a Hopf algebra structure. So, we here conjecture that the availability of a Hopf algebra interpretation for a given scenario within the relative locality framework is connected to the validity of these four properties. So, we basically promote those properties that were extracted and are also, these properties are also present in the Sitter momentum space in the Kappa-Poincaré formulation, and we promote them to axioms in such a way that we could explore the 4D kappa anti-de Sitter momentum space. Basically, assuming R1, R2, and R4B, we found that the only composition law that could be defined is this one. However, it is not associative. Oh, it is not possible to find a composition law in 4D that satisfies R1, R2, R3, and R4B. So we could move to R4 simply. Well, it is worth mentioning that if we follow this same procedure in 3 dimensions, there is a particularity of the dimension in which we can include the three-dimensional Levi-Civita symbol, where the composition law is exactly the one found in the momentum space of 3D gravity. Well, so we changed R4B by R4 by allowing a back reaction on the foreign Lorentz transformations, and we find that the composition law has the form, and it is unique. And however, it possesses singularity on the denominator because it can be 0. And then you ask whether this is a problem of the formalism of the composition law or if this is just an artifact of the coordinates. So we send the singularity to infinity, but unfortunately we recover it into the definition of the Lorentz transformations that had that strange form, but it's very common in this literature, especially in Kappa-Poincaré momentum space. And that condition, the one that I signed there, it's always solvable, which makes the Lorentz transformation ill-defined. Therefore, the composition law that satisfies all that set of axioms does not exist. That is, a Hopf composition law, as we stated, in 4D anti-de Sitter space does not exist. It does exist in 3D, but it does not in 4D. Curiously, if we follow the same procedure in the Sitter momentum space, we find kappa Poincaré momentum space. So that's why we consider that set of requirements very appealing to follow this axiomatic construction and this geometric survey through these composition laws. Well, that's the main result, but we also considered and listed some alternative formulations in which it appeared some, let's say, some anti-de Sitter form of some alternative composition laws or known in de Sitter momentum space. For example, we drop associativity, or we can drop isometricity, and we get anti-Snyder momentum space, because the Snyder was known, so we get the anti-Snyder. We can get a proper anti-de Sitter momentum space, because the proper de Sitter is known. And we also played a little bit with these requirements for complementary reasons. And also, we considered a different approach, the one inspired by Magejus-Moulin's composition law, and it turned out to be a map between different momentum spaces. But our main result would be the non-existence of a Hopf composition law in 4D, anti-de Sitter space. Well, this closes our momentum space part of the analysis. And we move now to a second part of the presentation, which is the space-time that could naturally describe these non-trivial features of modified dispersion relations that appear. So, what do I mean by could naturally describe? I mean, for example, having a dispersion relation as a norm for a metric in that space-time. And then this work was responsible for building a bridge between this formal metrics formalism and rainbow gravity. This was not the objective. It was a surprise at the end. But, well, to consider these formal metrics are that kind of metric that's a disformal transformation on a metric tensor, where alpha and beta are scalar functions, V is a vector field, so we introduce an external vector field. As you can see that the norm will be modified. So this formalism is used in many approaches, but in classical gravity, but it has never been used in the kind of approach that we described. So, explicitly, that's a disformal transformation for the covariant and contravariant metric. And while we were studying it, we discovered a group structure in that kind of transformation that closed the group operation, an abelian group. So we stopped a little bit about the modified dispersion relations, and we began to investigate this group operation and this group structure. How? Because we wanted to know how that operation appeared, what was exactly the reason. So we decomposed the disformal transformation on a metric tensor in terms of an operation on the tangent space. So instead of performing a disformal transformation on a metric, we considered a disformal operator. That's the machinery that we discovered. Also for the disformal cometric that transforms in the inverse way as the disformal metric, you can see. And then using this formulation, we proved a series of results, a series of propositions regarding ambiguities and uniqueness that appeared. And we also explained the nature of the group structure using this approach. But since this is not essential for this presentation, I will let it in the thesis and we will explicitly talk about it here. Something that I will explicitly talk is the causal structure, because now we get more physical insight. And then, well, we could classify the causal structure in terms of the beta function. That was this classification work that usually appears when one performs this kind of transformations on matter fields and So we also performed in this case. Well, this causal structure, as you can see, it basically states that it's how your light cone, if it lies outside or inside the background one. So, for example, here in this figure, you can see on the left that the light cones are changing. Therefore, the metric, that's the disformal transformation on the metric. So one light cone lies inside the other. And on the right-hand side, you see the same effect, where you keep the metric, but you disformally transform the vector. That's the action of the D operator. Well, this argument about changing light cones or changing vectors and changing the nature of these vectors, there is a map between this kind of language and the one that I was referring to for the energy-dependent speed of light. Because in that case also you would have photons traveling with, let's say, superluminal or subluminal photon, let's say, depending on the energy, of course. So, in fact, we found a relation between those transformations on a general metric tensor and the so-called rainbow gravity approach, which is a modification of general relativity that takes into account the DSR approach, but instead of working on curved momentum space, works on a transformation on the momentum coordinates or variables and makes it induce an energy-dependent metric probed by high-energetic particles. For example, in their case, it is considered this UMAP, for example, that transforms the momenta like that, and then the modified dispersion relation is calculated like this, with this standard metric. And, well, although this deformation was initially intended to take place in the Minkowski space, the idea of rainbow gravity is that such modified dispersion relation can be described by energy-dependent tetrad fields. Therefore, you get an energy-dependent rainbow metric of this form that transforms in the inverse way as the momentum space, or as the momentum coordinates. So, this U transformation here that acts on the momentum is very similar to the D tilde that we defined on acting on the cotangent space. So, in fact, that U and this D can be identified if we identify these functions, alpha and beta, like this. And in fact, it is the modified dispersion relation can be calculated with the disformal co-metric, which in turn induces a disformal metric and a rainbow-like metric if one identifies those functions. Well, we managed to write these functions intrinsically using only geometrical tools. So, therefore, this approach is covariant under coordinate transformations, and it gets the best of two worlds because it is covariant under coordinate transformations due to this formal structure, and it gets the covariance under the formal and local Lorentz transformations on the energy-dependent tetrad fields due to the rainbow gravity approach. So it is fully covariant from the point of view of the modified dispersion relation. And we also showed some examples from the literature where we show the compatibility of the causal structure of rainbow gravity with the classification of the causal structure that we did before about the beta function. So this way we managed to connect these two communities. And, well, but this approach, now I'll prepare for the next set of slides. This approach is very direct in the sense that it transforms the momentum, it transforms the metric, but we wanted something a little bit smoother in the sense that we wanted some variational techniques and work about geodesics and let's say use a variational definition for the metric and see whether it was possible to find a rainbow metric from other approaches. And indeed, there is. So that's where we enter into the last part of velocity-dependent metrics. And it was proposed in 2007 by Girelli, Liberato, and Zindoni, this paper that connects modified dispersion relations and Finsler geometry, which is basically you get a metric that depends homogeneously on velocities. So it's a metric that depends on the whole tangent bundle. Well, and also was further explored in a recent paper that explored the symmetries of these metrics. In this case, the modified dispersion relation is calculated from a norm, because the Finsler geometry is basically Riemannian geometry, but without the quadratic restriction. Therefore, you can have a norm with terms that goes like third power or fourth power in the energy, for example, or in the norm of the vector. So this way it can accommodate modified dispersion relations. So in this construction, the modified dispersion relation is also found from a norm. The geodesics of this metric give the world lines that are found in the Hamiltonian formalism, and the Lorentz transformations are the isometries of this manifold. So, in this thesis, we generalized the results that were presented in the previous papers by considering a curved space-time, because initially it was constructed on a flat space-time, but having a velocity-dependent metric. So we wanted to get a metric that would depend on coordinates and on velocities. So we managed to do it, and the construction is straightforward. That's the action of the Hamiltonian formalism. We just find the equations of motions, perform the Lagrangian transform, minimize the Lagrangian with respect to the Lagrangian multiplier, define the Finsler function like this, and then get the Finsler metric. So that's where you can see that the metric depends on the space-time coordinates and on the velocities. So it's defined on the tangent boundary. So we can reconstruct the action like this, which gives these geodesics. And the solution for the geodesic equation is equivalent to the solutions that are found from the Hamiltonian formula for massive and massless particles. In that formalism, for on-shell particles, you can substitute from the equations of motion the velocities by the energy and momentum. In this case, of course, we are working on 1+1 dimensions for simplicity. But the metric gets that form. And there is a feature here that was not present in the original rainbow gravity formalism, which is the presence of the mass of the particle in the definition of the rainbow metric. Therefore, it remains a question, what is the rainbow metric probed by massless particles? Initially, the rainbow metric was intended to depend just on the ratio of the energy or momentum of the particle and the Planck energy. But now there is a mass. And we wanted to see if it was possible to generalize the Finsler construction in order to, or at least give an alternative formulation, in order to have a Finsler or a velocity-dependent metric that had a smooth limit between the massive and massless cases. And we've identified where was the origin of this feature, and was that the metric was read from the Nembo-Goro-like action, from the arc length. So we proposed to read a metric from the Polyakov-like action that we know that is valid for both massive and massless cases. So this is our solution. We follow the same procedure, and we consider that one, the Polyakov-like action, the third line. So, and we define the metric G tilde as Taylor expansion in the velocities, and because we wanted also uniqueness So we get a metric that is also invariant in the reparametrization for the massive case, as should be, and it has that form. And for the massless case, one cannot solve the Lagrange multiplier, but we can absorb it into the definition of an affine parameter, which gives the action that is well known from, that is the known action used in general relativity literature. So both these actions, when extremized and give the geodesic equations for this metric, furnish also the same word lines that were found before, and is also the same as the Hamiltonian case. So we can also find our rainbow metric by the same procedure, and we find that here you can see that the mass does not appear in the definition of the metric. Therefore, in this case, it would be a little more close to the original rainbow gravity approach. But of course, this is an alternative formulation. And the mass, the dispersion relation is read also from a norm. So this way the mass does not appear. Well, this is the formal structure of this. So we wanted to give a step forward. And we considered some possible phenomenology for that. And then followed the intuition that to preserve the equivalence principle, that is, particles follow the geodesics of that space-time, the metric that an observer assigns to the space-time should be of rainbow nature. Therefore, using these insights, we calculated a formula for the time delay that measures the difference in time between two particles, the arrival of two photons that are simultaneously emitted from a GRB. And we found the left-hand side expressions, while the usual used approach by the paper of Jacob and Piran is the right-hand side, and of course it is used a different ansatz. And in any case, this proposal is falsifiable because you can compare and see if data fits better in which proposal. Well, we also calculated the redshift, in which we only needed to use the geodesics of the space-time. We also calculated the composition law from the point of view of the tangent space, and we also derived the relativistic transformations, the Lorentz transformations, from the isometries of this velocity-dependent metric. Well, just to close here, so in the first part we considered the curved momentum space to talk about half of the space, and we worked on the 4D anti-de Sitter momentum space guided by the intuition from 3D gravity. We axiomatically constructed a Hopf composition law, and we found that it was not possible to find a composition law with the features that are common in the most appealing approaches to this curved momentum space paradigm. And we also present some alternatives. In the second part, we worked on the space-time sector, where we managed to build a bridge between the Mageia-Molin's rainbow gravity and this formal metrics community. And we also studied group structure and all the algebraic interesting results that we discovered there. So, and to end, we worked on a more variational way of thinking of Finsler geometry and alternative formulations for velocity-dependent metric. We also propose an alternative ansatz to the calculus of observables in this kind of space-time, which allowed us to give a prediction about the time delay, which is different from the usually considered. For the redshift, which is equal because it only uses the geodesics. And we also studied the relativistic properties, and we realized that it's all compatible. The relativistic properties of the Hamiltonian are the relativistic of the dispersion relation, of the DSR way of thinking that, are the relativistic properties of the metric. Therefore, this board is complete. Well, of course, there's also a lot of work to do on this subject to continue on these projects, and I expect to give some more results soon. Well, thank you very much.